14-hour time difference. Anyway, all that aside, I'm very pleased to finally got him here. Eiji is an old friend of mine. Emmanuel used to, I'm sure. He got his PhD in 1979, I believe, from Nagoya University. And then, I guess he were postdoc for a year or two there. And then went to Australia for a couple of years. And then to Eiji in Masayama, which is, of course, a very nice spot in southern part of Japan. I think you spent 6 years, something like that,
yes.
until 1988. And then Tohoku University, which is much further north than Eiji is, and much colder climate. I've been in both places. I went there as an associate professor back in 1988, and I was promoted and said all sorts of very nice things. I'm not going to go through his long list of awards and all that kind of stuff. There is a lot of them. His interests are partly reflected in today's title. He's also interested in extraterrestrial problems, meteoritics, and so forth and so on. I don't want to speak about that today, but beyond not going any further about that, let us start with the volatiles in the interior of the Earth. So
thank you very much. I'm Eiji Ohtani from Tohoku University in Japan. And today I'd like to talk about these volatile issues. And this is my research activities. One is I'm very interested in the Earth and planetary core to do some equation of states and some velocity measurement, and also that the volatile issues. And also I did some experiment on the melting. And also the interested in impact processes, studying the meteorites and polymorphs in meteorites. Today I'd like to talk about the volatile issues and also sometimes volatile motion and circulation in the mantle, and also its relation to the Earth core. And in order to make this kind of research, I have some support from GSPS until the 2019, and also we are doing some collaboration in Novosibirsk University, and where I got some grant. And the recent several years, I'm working to establish some high pressure laboratory in Novosibirsk University. So this is our groups in Novosibirsk, and this program continues until 2017, but because of the financial problem, actually this program continues, but we have no grant next year, and we need to apply 1 year grant additional. And this is this grant covers many fields of high pressure and calculation and analysis of recovered samples. And this is multi-angle press system which we installed at Novosibirsk. And this is they break the windows to install this machine. And this is a theme of multi-angle press. And this is currently they are working using that press. Well, I'd like to start my main topics here, and especially concentrate on the water transport into the deep ocean interior. This is temperature and pressure, and this is the stability field of hydrospaces. And this is about middle of the upper mantle, about 6 GPa, that's 200 kilometers, there is a depression of the stability of hydrophases. And this is a white curve with many slab geosans. And people believe that this is the choke point, and not so much water can be transported into the deep upper mantle. However, there are several minerals which can be stable above the choke point. One is 10 angstrom phase and magnesium sarcasite, which is stable above the choke point. And also that newly reported high pressure polymorphs of hydrous perovskite, which is also stable above the choke point. And we did some stability experiment of this perovskite phase, and which can be one of the important carrier of water into the deep upper mantle. And also that even above the choke point, we can find that isolated fluid pocket can be stable. If you put some amount of CO2, the angle of the fluid pocket is greater than 60 degrees. And also with increasing pressure, some dihedral angles becoming greater than 60 degrees. So the water pocket can be moved into the deep upper mantles. And also that there are some non-phase, nominally anhydrous phase can contain some amount of water which can transport water into the deep interior. So we need some partitioning of fluid and non-phase. So it is very important to transport water into the further to deep upper mantle and transition zone. And also that so that in the transition zone can be very wet and heterogeneously contain water, 0.1 to 1% because based on seismic and electrical studies. And many people know that hydrothingolite was observed in the transition zone, which contains about 1% water. And also that phase X is also reported by Richard Bart, and this phase is also stable under the transition zone pressure conditions. So this is also the inclusions in kimberlite diamond. And stability of phase X is very interesting, and this is all our studies which limited the transition zone conditions. And recent report from Virus says that this is stable up to the top of the lower mantle. Our recent studies says that it is stability limited in the transition zone, so that this phase X is a signature of a hydrous transition zone, not the lower mantle. So this is a summary of the stability of hydrous phase, and also that in the upper mantle, transition zone, and lower mantle. It is interesting to see that there are several dehydration zones in the mantle transition zone, and the top of the transition zone and bottom of the transition zone. And also within the transition zone, slab stagnant and gradually heating up, then dehydration reaction could occur within the transition zone. So that this is our model of the slab subduction, and we can see the stagnant slab, and with heating up, the dehydration reaction could occur. And also that we did some experiment of the melt density And even hydrous melt can be denser compared to the surrounding mantle density. So we can expect some kind of dense melt at the top of the transition zone. So this is our model of the mantle transition zone. And recently, we can see some seismological observation at the bottom of the transition zone by Schmann et al. And this is also very expected due to the stability of the hydrous phases at the top of the lower mantle. And we need to study more about this kind of dehydration reaction. Let's move on to the further deep interior of the mantle. So this is a cartoon of the subducting flood and stagnant soil conditions. And stagnant flood eventually collapse into the deep core mantle boundary conditions, and we can expect that some of water can be transported into the base of the lower mantle. This is a more recent model of the formation of a super downwelling based on the formation of a supercontinent. This mechanism can also provide a lot of hydrogen into the core mantle boundary conditions. So it is quite important to consider about the existence of hydrogen into the deep lower mantle and the core mantle boundary conditions. And there is several candidates of hydrogen carriers into the lower mantle, such as phase D, superhydrous phase B, and nominally anhydrous mineral like aluminous distrobite, and phase X and aluminous phase D. But important hydrous minerals which transport hydrogen into the deep lower mantle is phase delta, ALOH phase, and those phase H, which is the isostructure, magnesium 3 silicon O2 OH2. And these minerals form a complete solution at high pressure and high temperature conditions. So these are very important water carrier into the lower mantle. This is the structure of the hydrous phases and phase H. And the structure is quite similar to distrobite or CaCl2 type SiO2, and the silicon side is occupied by aluminum and plus silicon, aluminous and hydrogen. So this structure is quite remarkable and stable up to the very high pressure and high temperature conditions. And this structure have phase transitions at around 15 GPa, and from different symmetry, and it is related to the symmetrization of OH bonding. So with increasing pressure, the hydrogen can be becoming symmetry. And this kind of symmetrization of hydrogen bonding is observed in water ice and also many other high pressure hydrophases, including phase D and this delta ALOH. So dense and high, so this kind of symmetrization provides dense and high sun speed velocity of these high pressure hydrophases. So our delta phase is becoming due to symmetrization of OH bonding. Follow this reaction, this line. This is OH bonding length, and this is OO bonding length. This line is just symmetrization. So that this delta phase moves, something like that. So it's becoming OH bonding becoming symmetry. Well, this is the stability field of end member of MgSiO2. And this is pressure and temperature. And this end member phase is stable up to 60 GPa. And the temperature around 1600 Kelvin. So this is deep, stable hydrous phases in the deepest to the lower mantle. This is stability field of phase D, and this is superhydrous phase D. So this phase. And hydrous phase is stable deep into the lower mantle. This is end member delta ALOOH phase. Again, this is very stable up to the core mantle boundary conditions. This is 135 GPa. This is core mantle boundary. This is temperature, and this delta ALOOH end member phase is stable up to 134 GPa and 2000 Kelvin, which is very effective, very good candidate to transport hydrogen into the core mantle boundary condition. This is a recent report by the Boulder et al. They also studied this aluminous hydrous H phase and shows the stability field covers to the base of the lower mantle. This is mantle geosam, and this is wet solidus under these conditions. Our result is quite consistent with their result. And this is our phase diagram. This is pressure and temperature conditions. And mantle geosam is here. And this is the stability field of hydrous phase H. And with increasing aluminum content, the stability extends to the deeper and deeper. At the base of the lower mantle, this hydrous phases contain 0.23 more percent of H phase and 77 more percent of delta ALOOH solutions, becoming alumina rich, but it is stable up to the base of the lower mantle. And also the stability field extends to the higher temperature. So aluminous delta phase, or aluminous phase H is quite stable up to the base of the lower mantle. This is a coexistence of two phases, Bridgmanite and this delta phase, so aluminous phase H. Clearly, we can see the coexistence of the two phases at 6 AGPA around 2100 Kelvin. This is a recoverable sample from a diamond W cell. And also these are the result of multi-angle press. Again, 20 AGPA and about 1573 Kelvin. We can see coexistence of delta phase, so aluminous phase H and Bridgmanite. Here is also we can see coexistence of phases. It is very interesting for the composition of the coexisting Bridgmanite and this hydrous phase. The partitioning of aluminum is interesting. Aluminum selectively partitioned into this delta phase. And so under the dry conditions, mantle and bridgemanite contains about 20% of aluminum. But quiescence of this hydrospace reduces aluminum content in bridgemanite, which can be a very important implication to the mantle chemistry. So the existence of water can change the bulk aluminum content in the lower mantle. This is analysis of recovered sample from 128 GPa and 2190 Kelvin. We can see the coexistence of delta phase and bridgemanite, post-perovskite phase. And under this condition, post-perovskite phase and this hydrophase is stable. And post-perovskite contains very small amount of alumina. In this case, 5 more percent of alumina, which shows the effect of water and for the lower mantle composition, bulk composition of lower mantle. And this is our recent result of the stability of hydrous phase H. So this is pressure and temperature, and we did experiment on peridotite water system and molar water system. And we observed that in peridotite system, the hydrous phase is stable up to 60 GPa. But in the molar oceanic crust, this phase is stable up to more than 70 GPa at the base of the lower mantles. And also that it is very interesting, the stability of this phase is very high, and this is stable up to the normal mantle temperature conditions. Usually this is a slab geosand, and hydrophase is only stable under the cold slab condition, but this phase is quite stable up to the normal mantle geosands. So that this phase can produce hydrogen into the mantle transition zone, then stagnant slabs collapse to the core mantle boundary. So this phase can react with the core. So that this interaction of the core and this phase is quite interesting. And also that the core mantle boundary is quite steep temperature gradient. So somehow the dehydration reaction or partial melting could occur under the core mantle boundary conditions, which is very interesting issues to be studied. So this is core mantle boundary conditions, and this is the pressure and temperature. And this is dry solid melting curve by PK and Andro. This is wet solidus by Nomura. And this is wet solidus reported recently by Mike Walker. So these are the dehydration regions, and partial melting should occur at the base of the transition zone. This is mantle geosands. We can see very steep geosand because of the heat flow from the core. So that this region is quite important. So that this is cartoon by Ray, and this is the core and base of the lower mantles. The core subducting slab and hot flues move upwards. So the temperature distribution at the core mantle boundary is something like that. In core subducting slab, the temperature is somehow increases rapidly at the core mantle boundary. This is the depth and temperature. So that the descending slab have to be dehydrated. And dehydration zone could be formed at the base of the transition zone, and also that wet melting could occur at the chromatic boundary, so that the hydrogen transport could be very important implications. So that the hydration of aluminous phase can be formed at the chromatic boundary, and those hydrous melting could be occurred. Could be potentially the origin of the low velocity zone. And also the reaction of, with the core is also a very important issue. And we studied the sound velocity of this hydrous phase, which is very interesting because under the low pressure conditions, this phase, shear velocity is relatively high due to the symmetrization of the OH bonding. But if we go to the quantum boundary, sound velocity is relatively lower than ferropericles and bridgeman. So accumulation of this hydrous phase can produce lower sound velocity regions. So that this is a seismological model of the core mantle boundary. This is a core mantle boundary. We can see this is VS velocity. We can see low velocity zones, which can be explained by some amount of accumulation of this delta phase, which can be formed by the hydration reaction. So that we can expect the hydration region at the base of the core mantle boundary. And this is existence of about delta H3 solution at the core mantle boundary conditions. So that we can expect that the hydration zone, then we can expect the hydration zone at in the mantle. Three distinct regions: base of the upper mantle, top of the mantle transition zone, and also the base of the mantle transition zone, and the top of the core mantle, lower mantle, and also the base of the lower mantle. Base of the lower mantle is very important areas of hydration zone. And also that I'd like to talk about this iron-water reaction. At the core mantle boundary, metal and water can be reacted with it. And as a result, we can get iron hydride here. Here is iron hydride and FeO. And this is our result of the metal and hydride phases at high pressure and high temperature. And we observed iron hydride due to the reaction of hydride phase and metallic iron nickel alloy. If we go higher pressure and higher temperature at the core mantle boundary conditions, we observed iron hydride. So iron hydride is very important to be as hydrous minerals and the outer core. So this mechanism transports hydrogen into the Earth core. And we did several different experiments of the reaction of iron and water, which forms FeO and FeH. And we expect this kind of reaction with the core mantle boundary conditions of the icy planets like Ganymede or Io. And also that we did reaction of iron and hydrous ringwoodite. And hydrous ringwoodite become dry, and if iron exists. And we can expect iron hydride and dry ringwoodite. And this reaction could occur in the Martian mantle, because in one model, the Martian core is contact with ringwoodite lower mantle. So that this reaction could work to bring hydrogen into the Martian core. And this is delta ALOH, and aluminum phase H could be the same, which produce again iron hydride, which could produce move hydrogen into the core mantle band, into the core. With this reaction of Fe3C, FeS, and FeS with water, but hydrogen hydride formation is very limited in case of these compounds. So this is a model of the mass. In Martian mantle, the core is contacted with hydrogen nuclides, and is becoming dry. And this reaction is also very interesting. I show that there is some reaction at very low pressure. Iron and water can form iron oxide and hydrogen. And if we go higher pressure, iron hydride and FeO is formed. And we confirmed this reaction. And also that FeO and H2O, FeO and H2O, this reaction is very famous Shiko reaction, which produces hematite and hydrogen. And this is also occurred at the surface of the Earth. This is well studied. And also that serpentinization could produce hydrogen. This again, in magnesium end member, there is nothing occurs, but in the Fe end member, pyrite and water react to form magnetite, SiO2, and hydrogen. This is very important for the hydrogen formation due to serpentinization. This is a well-known phenomenon. And I can suggest some similar reaction of FeO and H2O to form hydride, magnetite, and the high pressure serpentinization could produce FeH. So that FeH is quite important for the deep upper mantle, tension zone, and lower mantle. So this reaction is tie line is FeO and H2O, and low pressure magnetite and hydrogen. It's Shiko reactions, but it can tie line even shallow upper mantle. This is our preliminary experiment. Shows higher pressure we observed iron hydride, but need to be more experiment. And suspect that the shallow level hydrogen can be formed, but if we go deeper mantle, iron hydride is quite important. And we suggested that under the lower mantle, the garnet perovskite transition create metallic iron, so that again iron hydride is formed under the top of the lower mantle, which is very important candidate, important constituent in the whole mantle conditions, including upper mantle and tension zone conditions. So that hydrogen can be formed by the reaction of the core, hydride can be formed, the core and mantles. So that we need to study the hydrogen content in the core. And we did some experiment on the sound velocity measurement using elastic X-ray scattering. And we want to know how much hydrogen can be existing in the core. Let's detect it, and the sound velocity could tell something about this hydrogen. So we did in elastic excess scattering measurement at spring 8. This is IXS dim line at spring 8, and we put some portable laser here, and we put some diamond annealing cell here to make sound velocity measurements by inelastic X-ray scattering. Recently we did several sound velocity measurements from FEH and pure iron and sulfide and FE3C and silicon alloy, ionic alloys. And we could measure very high pressure and high temperature conditions. And this is room temperature, density, and velocity of iron here. And our measurement is at this time 174 GPa and 300 Kelvin. This is inner core. So we can see straight line of the Barchi spot, no bending. And also this is previous IXS measurement by PK, and this is our result is inconsistent with this curve. And our result is consistent with nuclear resonance in elastic excess scattering of the MAO, and quite consistent with those data. And we are trying to make more higher pressure conditions so that we can want to achieve to the inner core condition. That is future issues. And this is our sound velocity measurement by using inelastic excess scattering. So we could observe the temperature dependency of Barchi's law in case of iron. So that we found out this is density and VP at assuming the inner core boundary temperature of 5500 Kelvin. Our data can be extrapolated to here. This is density of the HCP ion. This is the velocity of HCP ion, which is higher than plane inner core conditions. So we need to reduce density. It is well known, but we need to reduce velocity also, so that light elements need to be both needs to reduce sound velocity. That is very important observation. And we did some sound velocity measurement of iron hydride by using inelastic X-ray scattering. So this is dispersion curves, and which provides the density and velocity of FEH. This is HCP ion. So that this is the plane inner core. We can expect the mixing of iron hydride about 0.23 weight percent of hydrogen in order to explain this inner core density and velocity. But this is the maximum value because we can expect another compound such as silicon, oxygen, sulfur, something. So that this is can be summarized something like that. This is a plane inner core, and our measurement of SCP ion extrapolated to the core, inner core boundary conditions. And this is 300 Kelvin, and this is high temperature. The effect of nickel, sulfur, silicon, something like that. Carbon and oxygen is quite high sound velocity. This is hydrogen. So the hydrogen can be a good candidate for the light element in the inner core. So that so we can estimate the amount of hydrogen in the core. The outer core, in order to explain the density deficit, we have no data on some velocity, so that the density issue can be can estimate the hydrogen content, which is about 28%, FeHx 0.55. In a core, based on the sound velocity measure, 0.13. So we need this amount of hydrogen to explain the inner core density and velocity deficit, the outer core and the inner core. But this is a maximum, and this is because outer and inner core contains many other light elements. The important conclusion is that the core is not saturated in hydrogen. In case of the hydrogen can dissolve up to x1, so that this value is smaller than unity, so that the core is not saturated, so that the hydrogen can be transported into the core by the present process, so that the core is absorber of the hydrogen at present. So this is my talk. Thank you for your attention.
Questions?
So you're proposing that the hydrogen can put in the core by that mechanism, but there's no return from the core. So are we going to lose our hydrogen?
So that's a good question. But at present processes, if so hydrogen is introduced, the contact with water is contacted to the outer core, it can be the outer core can absorb hydrogen. So because of the amount is not saturated, so that its reaction should occur until the saturation. But I'm not sure in the hotter conditions. In the hotter outer core could remove hydrogen, but at present.
But then it's not a circulation. It is the hydrogen when to go down there, it's down. I mean, that would be a problem that eventually all hydrogen gone.
That's a good question, but seismological model say that this kind of
So it's kind of related. I mean, obviously, this data phase sounds very interesting and it has a stability. But if you look at the overall Earth's compositions, and you need a very high aluminum content for the bulk Earth to be able to, say something about this would be a good, important mechanism, right? So because if you think about the salt peridotite, most aluminum probably can be dissolved in the bridgeminite, and
Yes.
there's an excess amount of data phase can form from that is highly depends on what is the bulk composition of
Yes,
the aluminum.
yes it is.
So you probably can do a back to envelope calculation how important this. And let's say we have 7 weight percent of alumina or 10 weight percent of alumina, and is that amount is a big sink into
Yes,
the process?
I think that is a good question, and we need to study more. And currently, we made some experiments using peridotite and water systems. And also that we made both basalt and water systems. Certainly, we need to be more variety of compositions, and the lower mantle could be more pyroxene-rich and not peridotitic, but actually we need to be studied. And also that this kind of experiment is quite tricky and difficult because the amount of hydrospheric is very limited compared to the diameter experiment because multi-component systems. So that we need to consider more careful experiment.
Is your data arguing against sulfur, silicon, and oxygen being potential components of the inner core?
No, I think that this is the maximum. I assume the maximum amount of hydrogen, so that if we consider the other like elements, this is the actual amount of hydrogen could be much less.
Okay. And you're not? Are you saying?
I am not.
Are you saying hydrogen is required to explain the velocity of the inner core?
I don't think so.
Okay.
Yeah, it seems like the key issue is what the partitioning of hydrogen will be between solid and melt throughout the whole depth of the Earth.
Yes.
I mean, it's possible that that you end up with hydrogen in the melt and dry minerals, and then depending on where the melt goes, when the melt is light and comes out, then it's going to not allow the hydrogen to sink any farther. But if you have a dense melt, then it might bring the hydrogen down towards the core.
Yes, exactly.
Is there any data on the partitioning of hydrogen in melt and solid in different conditions?
That is very important, and that is clearly needs to be studied. Yes. Because in that case, I think that hydrogen could be preferred to the melt, and the solid phase eventually could be very dry. But there are some experiment with partitioning experiment with metallic ion and silicate melt. So in that case, I absorb most hydrogen.
I have a question. You have FEHX. X is still for monohydride. What kind of phase? GHCP or FCC have you used in your estimates?
Is that DHCP? If you go higher pressure, become SCP. So we didn't make such high pressure.
So maybe this is something simple, but I'm trying to understand. You showed a plot where at the same density, you showed different sound velocities. So for example, hydrogen showed a lower sound velocity at the same density as iron, and carbon and oxygen at higher density. I don't understand why what causes that sort of and silicon, for example, sort of what causes that non-monotonic relationship. And then furthermore, I guess you're comparing the sound velocities from different chemical compounds with distinct compositions and crystal structures that appear iron. Is that really the right way to think about this problem, or would you want to have something dissolved in the same crystal structure, whereas the phonon dispersion relations would be completely different?
Yeah. I think that is a very important question, and the problem is the position or substitution of right element in metallic ion. In case of hydrogen, that is interstitial, and some other compound is also interstitial. On the other hand, if in case of FeO, Fe3C, that is in the isolated phases. So that in this calculation, we estimate just ideal mixture of two compounds, so that we need to be careful studies to check it, because the small amount of light element could be stayed in interstitial. So that kind of structural similarity have to be considered. So this kind of our estimation is very, very simple, naive ideal mixing of two compounds. So actually we need to be more studies with a small amount of, it needs some accuracy, difficult experiment. Yes,
So
very important.
that's
Yes.
the reason why the sound velocities.
Yes, yes, yes. Structure is quite different, especially in the case of FeO.
Thanks.
Anything else? Okay, I have two announcements for you. Thank you. One is lunch is served in ACC, so if you want to join for lunch, please show up in about 10-15 minutes. Second, at around 4:30 or so, we have something called postdocs to visit with the speaker in Boyd's. Anybody is welcome to come if you feel like it, to spend an hour or so with him. Yes, that's okay.
Yes.